When did dark energy take over the universe? For many years, the prevailing scientific understanding of our universe's destiny after the Big Bang was that its initial rapid expansion would inevitably slow down. This deceleration was expected due to the immense gravitational pull exerted by all the matter within the cosmos, a force that scientists once thought might even be strong enough to eventually halt the expansion and cause the universe to collapse back in on itself, in a theoretical event known as the Big Crunch. However, a truly groundbreaking discovery in the late 1990s fundamentally reshaped this cosmic narrative. Observations revealed that the universe's expansion was not decelerating, but was, in fact, accelerating, speeding up at an ever-increasing rate. This unexpected revelation was a profound shift in cosmological thought, compelling scientists to reevaluate the very dynamics and ultimate fate of the universe. It necessitated the introduction of a mysterious repulsive force, a phenomenon now referred to as dark energy, a term deliberately chosen to underscore the vast unknowns surrounding its true nature and properties. The central inquiry then became, when exactly did this cosmic shift occur, and how did dark energy come to dominate the universe? Dark energy operates in stark contrast to the familiar force of gravity. Instead of pulling objects together, it exerts a repulsive gravitational effect, actively pushing space apart and driving the accelerating expansion. It is essential to distinguish dark energy from dark matter, despite their shared dark moniker. Both are mysterious because they do not interact with light, but their cosmic roles are entirely different. Dark matter acts as an invisible gravitational scaffold, holding galaxies and other large cosmic structures together through its attractive pull. Dark energy, conversely, is the force propelling the universe's overall accelerating expansion. To truly grasp dark energy's overwhelming significance, one must consider the universe's composition. Dark energy constitutes an astonishing 68% of all the mass energy in the cosmos. Dark matter accounts for about 27%, while all the normal matter, everything we can observe, from stars and galaxies to planets and ourselves, makes up a mere 5%. This overwhelming proportion highlights dark energy's profound influence on the universe's past, present, and future trajectory. The very name dark energy reflects a deep scientific humility, serving as a constant reminder that while its effects are undeniable, its fundamental identity remains one of the universe's greatest unsolved puzzles. This deliberate choice of nomenclature acknowledges the profound mystery, particularly given the perplexing discrepancy of over 100 orders of magnitude between theoretical predictions for vacuum energy from quantum theory and the observed amount of dark energy in the universe. A most compelling evidence for the universe's accelerating expansion, and thus for the existence of dark energy, emerged from meticulous observations of a specific type of stellar explosion, Type 1a supernovae. These supernovae are invaluable to astronomers because they function as standard candles. This means that Type 1a supernovae, which result from the detonation of a white dwarf star that has accumulated too much mass from a binary companion, consistently reach a known intrinsic brightness. This principle is akin to knowing the exact wattage of a light bulb. By measuring how dim it appears from a distance, its precise distance can be calculated. Astronomers, utilizing instruments like the Hubble Space Telescope, observed these cosmic beacons in distant galaxies. The pivotal finding was that these far-off Type 1a supernovae appeared dimmer than they should have been if the universe's expansion was slowing down. The only logical conclusion was that their host galaxies were farther away than anticipated. This observation could only be reconciled if the universe's expansion was not decelerating, but rather accelerating, pushing these galaxies to greater distances over time. This robust discovery, confirmed with extremely high confidence, marked a watershed moment in cosmology. The reliability of Type 1a supernovae as standard candles provided a critical cosmic chronometer, allowing scientists to effectively map the universe's expansion history. by comparing the observed brightness, which indicates distance, with the redshift of the light, which reveals how much the universe has expanded since the light was emitted. Researchers could plot the universe's past expansion rate, directly revealing the acceleration. Further corroboration for dark energy's influence comes from the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This ancient light offers a snapshot of the universe when it was merely about 380,000 years old. Data from the CMB, particularly the tiny temperature fluctuations within it, indicates that the universe is spatially flat. This flatness aligns with a universe containing a significant amount of dark energy. More recently, a groundbreaking piece of direct evidence for dark energy was identified within the CMB itself through the phenomenon of gravitational lensing. As CMB photons traverse billions of light years, their paths are subtly bent by the gravitational pull of massive structures, primarily clumps of dark matter, along their journey. A universe without dark energy would have fostered the formation of more large-scale structures, leading to greater lensing of the CMB. However, scientists observed too little lensing in the CMB to be consistent with a universe devoid of dark energy. The observed amount of lensing was precisely consistent with the quantity of dark energy inferred from other measurements. This marked the first time dark energy was inferred solely from CMB measurements, adding a powerful, independent piece to the accumulating body of evidence. This demonstrates how the CMB, traditionally a probe of the very early universe, has evolved to offer direct evidence for dark energy's influence in the later universe, showcasing the profound interconnectedness of cosmic phenomena across different epochs. Additionally, the repulsive nature of dark energy impacts the growth and evolution of cosmic structures, such as galaxies and galaxy clusters. By meticulously mapping the distribution of these structures across vast cosmic scales, astronomers can further constrain the properties of dark energy and its role in the universe's evolution. The universe's history can be broadly divided into distinct eras, each dominated by a different cosmic component, a sequence dictated by the differing rates at which their energy densities dilute as the universe expands. Immediately following the Big Bang, the universe was an unimaginably hot and dense fireball. For approximately the first 47,000 to 50,000 years, its expansion was overwhelmingly dominated by radiation, primarily high-energy photons and neutrinos. This period is known as the radiation era. During this time, energy was so intense that matter and antimatter were constantly being created and annihilated. As the universe continued to expand, it cooled rapidly. The density of radiation decreased faster than the density of matter because radiation not only spreads out over a larger volume, but also loses energy as its wavelengths are stretched by expansion. Matter, however, only dilutes due to the increasing volume. Around 47,000 to 50,000 years after the Big Bang, the density of matter, both normal and dark matter, surpassed the density of radiation, marking the beginning of the matter era. For several billion years, gravity was the primary force shaping the cosmos. During this period, matter began to clump together, forming the first atoms, around 380,000 years after the Big Bang. When the universe became transparent and the CMB was released, over hundreds of millions to a few billion years, these atomic clouds collapsed under gravity to form the first stars, then galaxies, and eventually the vast, intricate cosmic web of large-scale structures we observe today. Throughout this era, the universe was still expanding, but its expansion was decelerating due to the attractive pull of all the matter. This deceleration was crucial as it allowed gravity enough time to pull matter together and form the structures necessary for complex systems, including life, to emerge. As the universe continued its relentless expansion, the matter within it became increasingly spread out, and its density continued to fall. Eventually, a new, mysterious force began to assert its dominance, ushering in the current dark energy era. the pivotal moment when the universe transitioned from a decelerating, matter-dominated expansion to an accelerating, dark energy-dominated expansion occurred relatively late in cosmic history. Specifically, this cosmic shift happened when the universe was approximately 7.8 billion years old. From our current perspective, this means the takeover occurred about 5 billion years ago. Other estimates, such as around 10 billion years later than the Big Bang or since about 4 billion years ago, generally align with this crucial late-stage transition. Before this point, gravity was the stronger force, gradually slowing the universe's expansion. But at this critical juncture, dark energy's repulsive force began to overpower gravity's attractive pull, causing the expansion to speed up. The reason for this takeover lies in the differing behaviors of matter and dark energy as the universe expands. As the universe grows, the density of matter, both normal and dark, continuously decreases because it is spread out over an ever larger volume. Dark energy, however, behaves fundamentally differently. If it is, as the leading theory suggests, a cosmological constant, essentially energy inherent to the vacuum of space itself, then its density remains constant even as space expands. Even if it is a dynamic field, like quintessence, its density decreases much slower than matter's. Therefore, as matter became increasingly dilute and its gravitational influence weakened, the constant or nearly constant influence of dark energy eventually surpassed the weakening pull of gravity from matter. It was not that dark energy suddenly appeared or gained strength. Rather, everything else became relatively weaker. This fundamental shift in dominance caused the universe's expansion to switch from slowing down to speeding up, setting it on its current accelerating trajectory. This gradual shift, rather than an abrupt event, was a continuous process driven by the differential dilution of energy densities. The takeover point signifies when dark energy's influence crossed the threshold of being the most significant factor in the expansion rate. This timing was not a mere coincidence. It was a necessary condition for the formation of complex structures, including galaxies, stars, planets, and ultimately, life itself. Had dark energy's repulsive force dominated earlier, it would have overwhelmed gravity's ability to pull matter together, preventing the formation of any stable cosmic structures. The delay in its dominance allowed the matter era to be long enough for galaxies and stars to form, evolve, and create the heavy elements necessary for planets and life. Since dark energy's takeover approximately 5 billion years ago, the universe has been on an accelerating path, and this acceleration continues today. This implies that structures not already gravitationally bound, such as distant galaxy clusters, will continue to recede from each other at an ever-increasing speed. Our own Milky Way galaxy and its gravitationally bound neighbors will remain intact. But the rest of the universe will appear to fly away from us faster and faster, eventually receding beyond our observable horizon. The ultimate fate of the universe is largely determined by the precise nature and future behavior of dark energy. While scientists have strong evidence for its existence, its fundamental properties remain one of the biggest mysteries. The most widely accepted scenario, if dark energy remains constant as suggested by the cosmological constant model, is the Big Freeze or heat death. In this future, the universe would continue to expand indefinitely, becoming progressively colder, emptier, and more dilute. Stars would eventually exhaust their fuel and die out, leaving behind cold remnants like black dwarfs and neutron stars. Black holes would slowly evaporate through Hawking radiation. Ultimately, the universe would reach a state of maximum entropy, a cold, dark, and lifeless expanse approaching absolute zero temperature. A more dramatic and violent scenario is the Big Rip, which would occur if dark energy's repulsive force somehow increases over time. In this catastrophic end, the accelerating expansion would become so overwhelmingly powerful that it would overcome all other forces. First, galaxies would be torn apart, then stars and planets, and eventually even atoms themselves would be ripped into their fundamental particles, literally tearing apart space-time. Conversely, the Big Crunch scenario, where the universe eventually reverses its expansion and collapses back into a hot, dense singularity, is considered much less likely given current observations of accelerating expansion. This would only occur if dark energy's influence somehow diminished or reversed, allowing gravity to regain dominance. The nature and behavior of dark energy are therefore the single most important factor determining the ultimate fate of the entire cosmos, dictating whether it ends in a gradual cooling, a violent tearing, or a speculative collapse. Despite the profound implications of dark energy, its true nature remains one of the greatest unsolved puzzles in cosmology. Is it truly a cosmological constant, a dynamic quintessence field that can evolve over time? Or does its existence signal that our current understanding of gravity, Einstein's general relativity, is incomplete? Scientists are actively pursuing these questions. Ongoing and future missions, such as the Dark Energy Survey, DES, the Euclid mission, and NASA's Roman Space Telescope, are designed to make unprecedentedly precise measurements of dark energy's properties and how it has changed throughout cosmic history. By peering deeper into the cosmos and refining our models, humanity hopes to unlock the ultimate secrets of dark energy, and in doing so, reveal the ultimate destiny of our universe.